In this talk, we're going to talk about how you can do some of this multiplication for polynomials, how you can do that by hand more easily than you might have done in the past. Many of you have probably seen synthetic multiplication, but I'm sure if you've seen it, you might be rusty with it, or some of you might never have seen it at all. So let's say the goal is to just multiply these two polynomials, 1 minus x plus 3x squared, and 2 plus 2x plus x squared plus 5x cubed minus 2x to the fourth. You want to multiply this second degree polynomial by this fourth degree polynomial. Well, of course, you could just write it out using typical rules of expansion. You could write 1 times this, plus 1 times this, plus 1 times this, plus 1 times this, plus 1 times this, minus x times this, minus x times this, etc., and go through all the terms. But we can do something that's very much like regular old multiplication of integers, and we call it synthetic multiplication now for polynomials, and I'll show you how it works. We'll start with this bigger one. There's no reason you have to put the bigger one first. It just kind of looks nicer. It's subjective. It doesn't matter which order, since multiplication is in fact commutative. And I'm going to represent that just by writing down the coefficients. I don't want to be writing the x's all the time. The coefficients are 2, 2, 1, 5, -2, and that's it. Now you have to be very careful to keep things lined up, because if I'm just going to write down the coefficients, the power of x has to be determined by the position. So this column, everything below it, will represent x to the zeros. Everything in this column, this 2, and everything I put directly below it will represent x to the first power. This column for x squareds, this column for x cubes, this column for x to the fourths. And for future columns, you'll see I'll be going to the right. We'll have the x to the fifth column, the x to the sixth column, etc. We'll see how many more we need. You can see our highest power will be x to the sixth, so I don't need more columns. But normally you won't write any of this. You'll just write these numbers down. I'm multiplying it by 1 minus x plus 3x squared. That's 1 minus 1, 3. So this first row of digits represents the coefficients of this second factor. This second row of digits represents the coefficients in that first factor. And I want to do the multiplication. Well, multiplying this entire polynomial on the right by 1 corresponds to multiplying this first row by the 1. And so I can just multiply 2 times 1 is 2, 2 times 1 is 2, then 1 times 1 is 1, 5 times 1 is 5, -2 times 1 is -2. So just if the whole thing were to multiply this second polynomial here just by that 1, well, I would get that second polynomial. That's pretty obvious. That's what I have here. But now I want to multiply the whole polynomial by the minus x. So I'm multiplying this row of digits by the -1, but because it's in this second column here from the left, I have to shift everything over. I take 2 times -1 and I put the -2 here, shifted over 1 unit to the right. This 2 times -1 gives me a -2 here. 1 times -1 gives me a -1 there. 5 times -1. This goes very quickly if you're not explaining everything. -2 times -1 is 2. And then we do the same thing to multiply this whole polynomial, this second factor, by 3x squared. How do we multiply by 3x squared? It's just like multiplying by 3, but we start by shifting over 2 units. So the 2 times 3 is a 6. We're starting by shifting over here into the x squared column. And then again, 2 times 3 is 6. Then we'll get a 3. Then we'll get a 15. It's certainly okay to have multi-digit numbers there. There's no carrying. We're just talking about coefficients for certain powers of x. And -2 times 3 is -6. So you do this product thing, and then here you just add by column. 2, 0, that's -1 plus 6 is 5. This adds to 10. You have -7 plus 3 is -4, 17, and -6. So this row of numbers represents my solution polynomial. What is the solution? It's equal to 2 plus 0 times x, so I'll skip it, plus 5 times x squared, plus 10 times x cubed. Then there's minus 4 times x to the fourth, plus 17 x to the 5th minus 6x to the 6th. And there we have it. Let's look at one more example. This is the generating function we had for the problem we looked at in the last lecture. The problem of, well, let me write it down. This is the generating function for how many combinations of length k do I have from this three-letter alphabet, A, B, C, with at most two A's that represent, this is first factor you can think of as representing the A's, 0A, 1A, or 2 A's, 2 B's, and 3 C's. Those are represented by the other factors here. And now we can compute this by hand. Well, we're going to have to do it in two steps. We'll first compute the product of the first two, which is very easy. I'll show you how we could do this real quickly. The first factor is 1, 1, 1. The second factor is 1, 1, 1. We multiply the 1, 1, 1 by 1, and we get 1, 1, 1. We multiply the 1, 1, 1 by this one, and we shift over to the right, 1, 1, 1. We multiply the 1, 1, 1 by this rightmost one, and we shift two spaces over, 1, 1, 1. And then we add 1, 2, 3, 2, 1. That was very easy. Now, at this point, I could write this as 1 plus 2x plus 3x squared plus 2x cubed plus x to the 4th, but there's no reason to. I can just carry it over. In fact, you could just kind of continue here, but I find that makes a big mess, so I prefer to carry it over. 1, 2, 3, 2, 1. That's the result from this first product. Now I'm going to multiply that by 1, 1, 1, 1. And of course, this is very easy. It's just 1, 2, 3, 2, 1. That's what I get when I multiply the 1, 2, 3, 2, 1 by this first one. For this second one, I shift over 1, 2, 3, 2, 1. For the next one, I shift over again. And for the last one, I shift over again. And then I add 1, 3, 6. Then we have 8, 8, 6, 3, 1. In other words, this means that the product is equal to this, which is 1 plus 3x plus 6x squared plus 8x cubed plus 8x to the 4th plus 6x to the 5th plus 3x to the 6th plus x to the 7th. You see a lot of this work here is just writing down the powers of x. That's why synthetic multiplication makes things much easier. You're just writing down the numbers. The powers of x are all contained in the place in the columns, the place where the number is sitting. So you really have to be organized and neat. That's not my specialty, but I can do it. So I'm sure every one of you can do that just as well. And you'll remember this generating function is exactly the generating function we had. If we want to know how many combinations there are of length 4, the answer is 8. That's with combinations from this alphabet with these conditions, at most 2 A's, 2 B's, and 3 C's. The number of combinations of length 5 is 6. All of the answers to all these questions for all the different K's are given by this one generating function, and we could compute that entirely by hand in what I would consider, if I weren't doing all this explanation at the same time, very, very simple computations.